Good morning, everyone. Our presentation topic is the application of linear system engineering in circuit analysis and traffic flow. Our group member are Guo Chunting, Zhang Zheyan, and Li Weiming. In this presentation, we will explain how linear systems are used to model and solve real engineering problems. We focus on two examples: electrical circuit and analysis and traffic flow modeling. The main idea of our presentation is that many real systems contain several unknown quantities. These unknowns may be currents in a circuit, traffic flows on roads, voltage loads, or other engineering variables. By using linear equations, we can organize these unknowns into a mathematical model. Then, by using metric form, especially AX equals B, we can solve the problem more clearly and efficiently. So our presentation moves from real system to solvable models and finally to engineering decisions. Now let us first explain why linear systems matter in engineering. Engineering problems often contain many unknown quantities. For example, in an electrical circuit, engineers may need to find unknown currents and voltage. In a traffic network, engineers may need to estimate the number of vehicles or different routes. In a mechanical structure, engineers may need to calculate different forces or loads. These unknown quantities are usually not independent. They are connected by physical laws, balance rules, or proportional relationships. For example, in a circuit, voltage, current, and resistance are connected by Ohm's law. In traffic flow, vehicles entering and leaving a junction are connected by the conservation principle. Linear systems are useful because they allow us to put these relationships into a clear mathematical form. Instead of treating each unknown separately, we organize all the equations together. Then we can use matrix methods to solve them. The objectives of our presentation is to explain how linear system can model, solve, and interpret circuit and traffic flow problems. We will not only show the equations, but also explain what the result means in real engineering situations. Before discussing applications, we need to understand what a linear system is. A linear system is a set of linear equations with unknown variables. Each equation contains variables such as x1, x2, and so on. The important point is that the variables appear only to the first power. There are no square terms, no products of variables, and no non-linear functions. On the left side of the slide, we show a general system of equations. It may look long, but the structure is simple. Each equation is made of coefficient multiplied by unknown variables, and the result equals a known value. The same information can be written more compactly in matrix form as AX equals B. In this expression, A is the coefficient matrix. It stores the number of coefficients from the equation. The vector X is the unknown vector. It contains all the unknown variables we want to find. The vector B contains the known values on the right side of the equations. This matrix form is very important because it makes large systems easier to organize, calculate, and solve. This slide shows the general workflow from a real engineering problem to a linear system. First, we start with a real problem. This may be a circuit, a traffic network, a structure, or another physical system. Second, we identify the unknowns. These are the values we want to calculate, such as currents, flows, or loads. Third, we build the equations. We use engineering law to balance principle to describe the relationship between the unknowns. Fourth, we write the equations in matrix form AX equals B. This type organizes the information clearly. Fifth, we solve the system and compute unknown vector X. Finally, we interpret the result. This is very important. In engineering, their goal is not only to get numbers, but also to understand what the numbers mean. The result may help engineers check safety. improve design, reduce congestion, or make better decisions. So the core idea is that linear algebra acts as a modeling language and turns real constraints into mathematical equations, and then turns mathematical solutions into engineering decisions. Now, my groupmate Zhang Zhenyang will explain the first application, electrical circuit analysis.
Okay, thank you. Now I will introduce the first application of linear system, which is electrical circuits analysis. In electrical engineering, circuits often contain several unknown currents and voltage. In a very simple circuit, we may only need to find one current. But in a real circuit network, there may have many branches and many loops, so there can be many unknown values. If we solve these values one by one without a clear model, the process can become complicated. Linear systems help us organize these unknowns into equations and solve them in a system way. There are three important laws used in circuit analysis. The first one is Ohm's law. It tells us that voltage is related to current and resistance. When resistance is fixed, voltage and currents have a proportional relationship. So this relationship can be written as a linear equation. The second one is Kirchhoff current law. It means that the total current entering a node is equal to the total current leaving the node. This is based on the conservation of electric charge. The third one is Kirchhoff voltage law. It means that the total voltage change around a closed loop is zero. By combining these laws, engineers can build a system of linear equations. The unknown can be branch currents or node voltage. After that, we can use matrix method to solve this system. Now, let us look at a simple circuit example. In this example, there are two unknown branch currents. We call them I1 and I2. Based on the circuit's relationships, we can get two equations. This equation shows how the two currents are connected with each other. Instead of solving the equation separately, we can organize them into a matrix form. The matrix contains the coefficients of the equation. The unknown vectors contain the two currents, and the unknown vectors contain the values on the right side. This matrix form makes the problem easier to solve, especially when the circuit becomes larger and has more unknown currents. For this example, after solving the system, we get I1 equal 1.875 and I2 equal to 2.25. This result shows that the second branch carries a larger current than the first branch. Now, let us discuss the engineering meaning of this result. In mathematics, we only get two numerical answers, but in engineering, the numbers themselves are not the final goal. Engineers need to understand what these numbers mean in the real circuit. Since the current in branch 2 is larger, the component in branch 2 may carry more electrical load. For example, the resistor or wire in that branch may heat up more. Therefore, engineers need to check whether these components can safely handle the current. If the current is too large, it may cause overheating, energy loss, or even damage to this circuit. So the solution helps engineers check overload risk and decide whether a larger safety margin is needed. 6 examples show that linear systems are not just abstract mathematical equations. They are practical tools for engineering design. By using linear systems, engineers can determine branch currents, check component stress, improve circuit safety, and analyze larger circuit network more efficiently. That is the end of my part. Next, my crewmate Li Weiming will introduce the second application, which is traffic flow modeling.
Okay, thank you. Now I'll introduce the second application, which is the traffic flow modeling. By the way, my name is Li Weiming, and my student ID is ECN2409004. Okay, let's get started. In a road network, traffic flows can also be treated as unknown variables. For example, x1, x2, and x3 can represent the number of vehicles passing through 3 roads in 1 hour. The basic principle is conservation of traffic flow. In a stable traffic situation, the number of vehicles entering the junction should equal the number of vehicles leaving the junction. This idea is similar to a balance equation. When we apply this conservation principle to different roads or junctions, we can form several linear equations. These equations describe how the traffic flows is connected. So just like in circuit analysis, we can use a linear system to model the traffic network. These slides give a simplified traffic flows network model. We use 3 unknown variables, x1, x2, and x3. They represent the traffic flows on 3 road segments. The unit is vehicle per hour. The 3 equations are x1 plus x2 equals 500, x2 plus x3 equals 420, x1 plus x3 equals 380. These equations describe the traffic relationships in the simplified network. Now we can write it in matrix form. The coefficient matrix A is 110, 011, 101. The unknown vector x contains x1, x2, and x3. The unknown value vector B contains 500, 420, and 380. To solve the system, we can use a simple element idea. If we add the first equation and the second equation, we get x1 plus 2x2 plus x3 equals 920. But from the third equation, x1 plus x3 equals 380. So we subtract 380 from 920. This gives 2x2 equals 540. Therefore, x2 equals 270. Then from the first equation, x1 plus x2 equals 500. Since x1 is Since x2 is 270, x1 equals 230. From the second equation, x2 plus x3 equals 420. Since x2 is 270, x3 equals 150. So the final solution is x1 equals 230, x2 equals 270, and x3 equals 150 vehicles per hour. Now, let's interpret these traffic results. The solution is not just a set of numbers, it can support real traffic decisions. Among the 3 road segments, x2 is 270 vehicles per hour, which is the highest flow. This suggests that this road is busier than the other 2. Traffic engineers can use this information to adjust signal timing. For example, the road with a higher traffic flow may need more green light time. The result can also help engineers identify possible bottlenecks before long queues appear. In addition, the result can support road planning. If a road segment has consistently high flow, it may become a priority for line expansion or traffic control improvements. Therefore, linear systems help traffic engineers identify busy roads, reduce congestions, and improve transportation efficiency. The example we use are small and simplified. However, real engineering systems can be much larger. A small system may be only 2 or 3 unknowns, so we can solve it manually or by substitution or elimination. This is what we did in the circuit sample and traffic example. However, real circuit networks, city traffic systems, structural model, and computer simulation may contain hundreds or even thousands of unknowns. For these larger systems, engineers usually use matrix methods and computer algorithms. Common methods include Gaussian elimination, matrix inverse methods for small systems, and numerical methods for large systems. In real applications, the coefficient matrix may also be sparse. This means many entries in the matrix are zero. Especially computational methods can make solving these systems more efficient. The important point is that the basic idea remains the same. Whether the system is small or large, engineers still identify unknowns, build equations, write matrix form, solve the systems, and interpret these results. Now, let's conclude our presentation. Linear systems are useful because they help engineers model problems with multiple unknowns and constraints. In circuit analysis, we use linear equations to find unknown branch currents. The results help us understand branch loading and possible safety concerns. In traffic flow modeling, we use linear equations to estimate vehicles' flow on different roads. The result helps us identify busier roads and support traffic control decisions. Both examples follow the same modeling structure. First, we model the real problem. Second, we organize the equations in matrix form AX equals B. Third, we solve the system. And finally, we interpret the numerical results. Therefore, linear systems connect mathematical theory with real engineering decisions. Finally, this slide shows the reference we used in our presentation. We used linear algebra textbook by Lele and McDonald's and by Gilbert Strand to support the mathematical concept of linear system and matrix form. We also use electric circuits by Nilsson and Riddle to support the circuit analysis background, and traffic flow fundamentals by May to support the traffic flow modeling background. These references are listed in APA 17 edition book reference format. So that's the end of our presentation. Thank you for listening.